Around 1897, scientists had a good idea that there were electrons in an atom. They had no clue where they were. By 1910, they knew that there was such a thing as a nucleus, and the electrons were outside the nucleus, but they didn't know where. Over the next 10 years or so, a big discovery was made where the electrons are, and it was done by a Danish physicist who knew a lot about light. We better review a little bit about light before we go into this discovery. So, for Screencast 5.3, we'll be talking about light and the electromagnetic spectrum before we get into how this applies to where the electrons are in an atom. This is Screencast 5.3. So what do you know about light? Here's some essential information. Number one, a British scientist by the name of Young, determined, I believe it was in the early 20th century, that if you pass light through two slits, it can create multiple lines on a back wall. Not an easy thing to replicate in a lab, but it sure does happen. I remember my physics professor, Lanny Brooks, doing this and showing it on the back of the wall. I've tried to replicate it myself, and it requires a pretty special setup, but it's true. And this is impossible if light is traveling in a straight line. I mean, it just can't happen. There must be something else going on. It makes perfect sense if you consider that light is traveling in waves. See these waves and how they're propagating? You throw them through two holes, they'll start to propagate again, spread out like this. And when they hit each other, they can lead to interference. We won't go into details such as constructive and destructive interference, but when they smack into each other, that can create a bit of a mess, leading to these lines here. And the clear conclusion is that light travels in waves. So that's going to be important. I hope that this simple experiment proves to you that this is the case. If it travels in a wave, we can come up with a formula for anything that travels in a wave. In effect, this formula really works. I was thinking about this recently for, even if it isn't a wave. But anyhow, the speed that this whatever it is traveling in is equal to the wavelength, how long the wave is, times how frequent it is. The speed of light is super fast, 3 times 10 to the 8th meters per second. It gets to the moon in, I think it was it under a second? It's like an amazingly fast time. And the longer the wave is, the faster it'll move. No, not the faster it'll move. It'll just have a longer wavelength. It'll be less frequent, right? Because the speed is constant. The frequency units are per second. That's an unusual units, but it just means how often. The wavelength units are the length of the wave, and they're typically in meters or some derivative thereof. Okay, so here's some high frequency waves with a short wavelength. Here's some long wavelength waves with a very low frequency. So short wavelength means high wavelength. It's high frequency. Those can be dangerous. These have more energy packed into them, and some of them can kill you. These waves are traveling much greater distances over the course of a wave. They have a longer wavelength. They pass by a given spot less frequently. Don't forget, they're still going 3 times 10 to the 8th meters per second, so the frequency will be high no matter what, because they, typically we're talking about 100 yards or something for some radio waves, but anyhow, they're much safer. Don't worry if you're being bombarded by radio waves, generally speaking. Let's go ahead and solve a problem for this. What's the wavelength of violet light? The frequency is 7.23 times 10 to the 14th times per second. So let's check it out. We want to solve for wavelength. The speed of light equals wavelength times frequency, so I guess if we divide both sides by frequency, we'll see that wavelength equals S over F. S is always 3 times 10 to the 8th meters per second. The frequency is given, and the answer should spit out in meters, and we get a 4.15 times 10 to the minus 7th meters. I should convert that to nanometers. I think that there are 10 to the 9th nanometers in a meter, but oh, there it is, 415 nanometers. And that's in the range 400 to 700 nanometers is visible light. So that's just a little bit about light, how it travels in waves, and how therefore it has a speed, a wavelength, and a frequency. And the speed is a constant. This is Screencast 5.3.